Okay. Hi, everybody. The subject of this lecture is the animation of the particle motion or particles motion of the detailed particle swarm optimization problem. In lecture number 16, we have animated the motion of the particles by using the library of pi swarms. We at first used the minimize function in order to find the minimum, and then we used the plot contour function, and we have seen how the particles converge to the point of minimum of the function. But at that time, we did not write or illustrate to you how the animation is carried out. Only we have passed the minimum required arguments to the function or to the model of PLT contour, and we did not know exactly what is happening inside that library. The subject of today's lecture is to know in a sufficient detail how animation is carried out to the particle swarm optimization algorithm. In order to remind you with the basics here, we are going to use matplot library for this purpose. We shall call from this library the class func animation, and this func animation requires, of course, some arguments to be passed to it. Also, of course, in order to animate the PSO, we need to, at first, to optimize it. And during optimization, we are going to have some data, such as the personal best position for every particle, the global best value or position for the whole swarm, and the fitness or the best fitness for each particle and the best fitness for the whole swarm. These arrays are generated through the work of the optimization of the PSO. At first, we usually show you the function which we are going to optimize. We are going to optimize Rosenbrock function. As you see, this is its plot, typical plot. The bounds are between -5 and 5 to x and y. And also, we are plotting the contour of this function, and I have overlaid on this contour the point where the minimum of this function is going to be. This is the point 1 for the x coordinate and 1 for the y coordinate, and it will be 0 for the third coordinate or the z coordinate. In order to plot this function, I first defined the objective function. It has two variables, x and y, as you see. We have also created two arrays, x and y, which represent the x and y coordinates in the range between -5 to 5 with 250 points, and the other y coordinate between -5 and 5 also with the same number of points. So, shortly speaking, we have defined the objective function, we have defined the bounds of the variables of this function, and then we used the NumPy mesh grid function, and also, of course, we have created a figure object and axis three-dimensional object here also, and at the end we plotted this function by using plot surface, where we pass the coordinates x and y and z. As a result of that, we achieve this figure. What is added here? I added this piece of code where we can define the minimum value, z minimum of the function, and its position in xy plane, and there we use the xtravel function and the argument minimum function to define the x minimum, and the same function for the y coordinates. We define the y minimum. We use the x minimum and y minimum and pass them to the function, Rosenbrock function. We get the z value. The results are shown here down. The x minimum is about 1, and the y minimum is about 1 also. These are the coordinates of x and y, 1 and 1, and the value of the function it will be around 0. Here it is. This red x represents the position of the minimum, and this position, it really is the point where we shall compare it with the motion of the particles during the animation process. The x value here is also equal to 1, as you see, and the y value is equal to 1, and the z value is equal to 0. If you note the values of these contours, as we are approaching more and more, we are coming to the 0 point here. I have added only 20 contours so that the figure will be clear for you. Now, as you see, I have reminded you how to plot the Rosenbrock and its contour, and this point of minimum is also overlaid on the contour plot. The second thing we are going to do is to remind you how we also optimize this particle swarm function, but by using the general detailed algorithm for that. We also are going to use the Rosenbrock. Rosenbrock function at this time is defined by importing it from the functions directory of the PySwarms. As I told you previously, PySwarms library has a directory called functions, and there is a lot of functions which could be used without defining them specifically. So I imported Rosenbrock from there, and now we shall begin optimizing this function. We have defined its dimension as 2. It has only x and y coordinates. We define the PSO algorithm with the required parameters, such as the name of the function, Rosen, the dimensions, number of particles, and the number of iterations. In order to carry out the optimization process, at first we need to create two-dimensional arrays. One of them which represents the positions of the particles, it is called their particles. This is X and Y position for each particle. And we are also creating another array, another two-dimensional array with zero-like function. And these values here are zeros, which represent the initial values of the position of the velocities of the particles. For each particle, there is a corresponding velocity. And now the optimization begins from here. So we have in our hands the positions of the particles, and we have the initial velocities of the particles. In order to find the personal best position for each particle, here we cannot compare these values with any previous values, so we consider the created particles positions as the particle best positions. So we make NumPy copy of the particles, and we assign it as the particle best positions. So this is a two-dimensional array which represents the best position for each particle now. Now, if we substitute the position of each particle in the function Rosenbrock, we can find a value which represents the fitness of the loss of the Rosenbrock function. It is called personal best. Here it is called personal best fitness. Some people write it as personal best object. It is the same. So, shortly speaking, now we have a number for each particle which represents the location or the best fitness for it. Now, having this particle best fitness, we can define from it the global best position and the global best fitness. To find that, we make use of the NumPy argument minimum or NumPy arg minimum function. NumPy arg minimum function, if you pass an array to it, it can give you the index of the value which is the minimum value in that array. Having this index in our hands, we can assign it to the best position array, then we can get the global best position. So this is the global best value already defined by using the arg minimum function. And now, as we have particle best fitnesses as an array, so we can use NumPy minimum, and we find also the minimum value here, which represents the global best fitness. So now we have in our hands four things, four arrays: the particle best positions and the particles best fitnesses. This is two-dimensional array, and this is also, and the global best fitness. This is one-dimensional array because it is for the one value, and the global best fitness, which is also one-dimensional array. In order to continue working with the algorithm, you remember we need to make use of the cognitive and the social coefficient C1 and C2, and to make use of the inertial coefficient, which is denoted by W. Here I have used these values. Of course, depending on the result which you can get, you can change them within the given limits of each. C1 and C2, you remember I said they are generally between 1 and 2, 0 and 2. W is around 1 usually, and you can get the required behavior of the PSO. Okay, now, in order, this is all what we have now as the beginning stage, as the first iteration. If we want to iterate the values, so we need to have new values for each iteration. First of all, we need to change the velocity of each particle. And for this, we use, as I told you, 3 terms. The first term, which is scaled by multiplying the velocities by the inertial coefficient. The velocities, you remember, we have created here it. And we add to this term 2 other terms. One term is C1 multiplied by R1. This is a random number between 0 and 1, multiplied by the difference between the personal best positions and the particles as the current value or the current position. And the other third term is C2 multiplied by R2 multiplied also by the difference between the global best minus the particles. So using this expression, which is really the bare core for the particle swarm optimization, we can achieve a new value for each, a new value for the velocity for each particle. Having the new values of velocities, we can realize or we can define new positions. So this is updated value now of the positions. Instead of particles, now we have another new value of the particles here. Now we can, as we have a new value for the particles, so we can make use of it, the new value, and consequently, we can also carry out the updating values for the personal best and for the personal best fitness and the global best and the global best fitness. Okay, so what we are going to do, again, we are substituting the position for each particle in the Rosenbrock, but now these positions are new, the new particles here, and we assign it to a variable, we call it fitness. And now we compare this fitness value, of course, for each particle with its best fitness. If this fitness is less, which is the desired condition while doing minimization, so we adopt this value, make a copy of it, and assign it as personal best position for each particle. And the fitness also is assigned as the personal best fitness for each particle. Concerning the global best position and fitness, we can also define them by using the already found fitness value by comparing it with the global best fitness, not with the personal best fitness with the global best fitness, and if it is less than the previous global best fitness, so we adopt it and assign it as a global best position, and the fitness is also considered as the global best fitness. So with this now we have, at this iteration, we have other 4 values for the personal best position and the personal best fitness and the global best position and the global best fitness. And we continue this going on until the required number of iterations upon desire. In order to get the values at the end, we run the PSO algorithm here and pass these arguments to it as they are passed here. So the function is Rosenbrock. The bounds are given here as between -5 and 5, -5 and 5. The number of particles is given as 30, and the number of iterations is given as 1,200. When we run this program here, we get the best fitness, which represents the minimum value of the function, and the best position, which represents the x and y values where the minimum occurs. So we get 1 and 1 and 0. If you want to see it, I can run it in front of you, and you can see that we have got exactly the same answer. This is the process of minimization, and here we do not yet tackle the issue of animation. Also, I wanted to show you another way of working with the minimization of the global, sorry, of the detailed particle swarm algorithm. In this case, I have defined Rosenbrock as a function, as you see here. I didn't use it as a function from PySwarms. And mostly the program here is repeated, but not exactly the same. Let us go quickly through it. So we have created the positions of the particles as a 2-dimensional array here. And we have created the initial values of the velocities. Then we have assigned the positions of the particles as the personal best. And now we have substituted the values of the best of these values in the function Rosenbrock and obtained the fitnesses. Here it is written as particle best object instead of fitness. It is the same, no difference. And now also we have derived from the personal best object or fitness, we have derived by using arg minimum function, we have derived the global best, and by using the numpy minimum function, we have derived the global best. So again, we have the 4 interesting values: the personal best value, the personal best fitness or object, the global best, and the global best object. Again, we are using the hyper values CY and C2 and W, and we have updated the velocity, and now we have got new values of velocities for all the particles. We use this value to update the positions. Now we have new positions, and now these new positions are used, the particles here are used in order to find or update the values of personal best position and the personal best fitness and the global best and the global best fitness of all the particles. And as you see here, some little different. We have made 4 loops by using the enumerate function of the particles, and we have substituted the Rosenbrock with the positions. We have added the positions in the function, and we have got the fitness. And again, we are comparing this fitness with a personal best object for each particle. And if the score is less, so we adopt it and we consider it and assign it as the personal best new value. And also the score here, which is the fitness, is assigned as the personal best score. The same thing, we also compare the score with the global best object, and we do the same and define the global best and the global best object. So in the second iteration also, we have now updated the values of the personal best fitness, global best fitness, and we are going to carry out all these things through the for loop until we cover the whole number of iterations. The number of particles, again, I have taken 300. The number of what else here I need? Number of iterations 1000 instead of 1200. It is the same, it makes no difference. And that's it. If I run the program now, let me run it for you. We have got, as you see, the positions is 1 and 1, and the best score or the best fitness is 0, and the results are exactly the same. These points, which we see here, are exactly the same points which we have got. It is this point, and they are exactly the same values which we have got by using the LabVIEW function as we did before with the arg minimum, the x LabVIEW and arg minimum. They give the same results. But here we have got the results by using an iterative process, not by calculation. Okay, now we are very close to our work. The target of this lecture, which is to animate the motion of the particles. So, of course, we are going to use the same function to be consistent with ourselves. We are defining the function as you see here. This definition is well known to us. We have defined also the bounds within the bounds of Rosenbrock. Rosenbrock between minus 5.12 to 5.12. I have taken it minus 5 and 5. I have used the NumPy a range with a step equal 0.15, as you see here, and the same thing here. And we have defined the value also of the function. All these things are known to us. We did the same before. We have also again defined the x minimum and the y minimum and the z minimum, because we need to plot the position of x and y and z, and to see how the particles converge to this point. So this is necessary for us, but I have derived them here and I printed them to be seen for you when you revise this material. This is the x value is really about 1, the y value is about 1, and the z value is practically 0. So we are still preparing for the animation work. Now we define the parameters C1 and C2 and W, we do that. Number of particles, we do that. And we create now the particles. Here X, this capital letter X represents the positions, the initial positions of all the particles. And the capital V here represents the velocities of all the particles. So for every particle here, there is a corresponding value which represents its velocity here. And the dimension of this array X and the dimension of the array V are exactly the same. And now we have only the values of X and V. As we did before, the values of X now are considered as the personal best values, and we use the personal best values in order to generate. First of all, we got for each value here, if X or personal best, but the same thing, we introduce or substitute each value in the function to get the fitness of the function for each particle, personal best object or personal best fitness. And now by using personal best fitness here with the arg minimum function, we can find, as I told you, the coordinate of the minimum value, the index of the minimum value, and this index, if it is assigned to the P best, we get the global best. And also using the minimum function, we can get the global best object or the global fitness. So again, here we have defined initially the 4 variables of interest here, which is the personal best, which is an array, 2-dimensional array, the personal best fitness, which is also a 2-dimensional array, and the global best fitness. These are also arrays, but not 2-dimensional arrays, 1-dimensional arrays. And now we want to carry out the animation. In order to carry out the animation, we need to make use of the update. So within this update function, we now change the velocity from the previous value, which is V, to a new value V, which is calculated as we did before by adding the 3 components together, as you see here. And the new thing for you here maybe is when we add the social, the product of the social coefficient C2 with the random value R2, with the difference between G best and X, here X represents the particles, the G best is reshaped to by -1 and 1. This technique is usually used to convert the G best to a 2-dimensional column, because it is 1-dimensional, as I told you, not more. So we get here a new value of the speed, of the velocity, sorry, of each particle, and we add it to X and assign it to X. We got the new position for each particle. So now, as you see, we have updated the velocity and updated the positions, and now we can make use of the updated positions. This X is 2 variable. It represents the X coordinate and the Y coordinate. X of 0 is the X coordinate, X of 1 is the Y coordinate. We substitute the value of each particle here in Rosenbrock to find the fitness or the object as it is called here. And now from this object here also, through the process of comparison, we can define the personal best and the personal best objective and the global best and the global best objective. How it is done as we did before, nothing new for you. Here we compare between the object which we have already found for each particle here with the personal best objective which we already has. If this one is less than 1, if object is less than P best object, so this is the case which we want and we must adopt it, and it will be considered here and assigned as the personal best value. Uh, also, we can, as you see here, define the personal best fitness. Here we used, as you see, the object here, which is already defined, and the personal best object. These two, this is an array, and this is an array, and this is a list of arrays. If we apply minimum for x equal to 0, really we get the minimum value, which is the smallest value between object or p best object for every particle. So we here p best object represents the minimum of, or the result of comparison, which is the minimum for each pair of them. Again, here we use the also personal best object, and through the arg minimum we define the global best and define the global best object. So again, here we have updated, as we did before, the personal best object, the global best, and the global best object. Now, in order to animate, we need to use the matplotlib function, which is called, or class, which is called func animation. This func animation requires to define in advance the figure which is going to be animated and the animate function which is going to be used, and we have to define the number of frames or animations which are going to be used and the interval in milliseconds between each two frames, and if we want to repeat the whole animation or we do not want to repeat that. So if we come back here, we have already defined, or we have plotted a number of plots which represent the personal best, which represent the global best, which represent the positions of the particles, and so on. So to have a figure in a figure defined for the func animation figure, we have to create a figure and an axis here. PLT, this is from Matplotlib, subplots, fixed size 8 and 6. Now we have defined the axis and we have defined the figure. Okay, then we are going to plot the minimum values which I have calculated here, the x minimum and the y minimum here. So we make use of the scatter plot, or just directly we use AX plot x minimum, y minimum. This is, there are 2 points only which we have. We assign to the point which is represented by this x value and this y value an x red one, it is called a marker, with a size equal to 5 and the color is white. So if we go at the result and see our result, it is this point here, which is marked. This is the marked point with white, and here 0, here 2. It will be with y equal to 1, and here x also is equal to 1. So we have, simply speaking, overlaid this point on the plot. Now we shall plot the contours of the plot by using x contour, and we pass to this x contour the parameters x, y, z. 20 is the number of the contours, color is black, alpha represents the transparency of the contours. So if you go to this contour, these are the contours. The color is black, as you see. and the number is 20. If you count 1, 2, 3, 4, 5, 6, 7, you will get 20. And here, as you see, the number of zero practically is in this very, let me say, dark area, which is in this position. And this area is the zero. This is the zero position exactly. Here I have put the really 20 maybe, as I accustomed 20 maybe. I will see how much they are, 20. I shall increase them for you. Let them be 100, for example, and we shall see later how they will appear. Next, we shall plot using the scatter plot the X positions. X here, the big X represents, of course, two values, the X coordinate and the Y coordinate. So we are taking for each particle the X coordinate and the Y coordinate, and we are plotting the particles, as you see, with a marker as an O, which is red. And here for just for making the plot interesting, we are using the AX quiver. This is a way to show a vector motion with a length equal to the value and components X and Y or U and V, which represent the X projection of the vector and Y projection of the vector. So X of 0, X of 1 represent the position of the initial point of the arrow, and V of 0 and V of 1 represent the components of the vector. After having this, we are going also to plot the most interesting point, which is the global best point, which is represented as a scatter between the global best 0 and the global best of 1. This will be also, as you see, an asterisk here. If you go back down here, we will see it here. This is the blue asterisk here, which is converging or coinciding with the white X. This is really the global best value. Okay, so now if we run the program, one more interesting also thing here, after animation, we normally save the animated figure. It is saved under the name Rosen3 GIF, and it is saved by using a writer called ImageMagick. ImageMagick, really, you have to download it yourself. I have downloaded from the site, from the internet. And also, in addition information for me, I have asked the program to print the global best value and the global best fitness. Here the position, and here is the fitness. Also, I have managed to show you the plot by using HTML, so you can see it by using HTML or by going to Rosen3 GIF file there and see it. Now let us try to run the program. When I run the program, of course, we have to wait maybe 2 to 3 minutes about that to see the results. So I run the program now. Now the program, as you see here, I shall show you. Here, this is the asterisk. It is running. The program is going on. And when it will stop, I shall show you the results. Not too much time. Really, the time, as I told you previously, it depends on the number of iterations which we are selecting, and also at the number of the particles which we are working with, and of course on the nature of the function, because if the searching area is very large, it takes also more time for that. But for Rosenbrock, it is not that complex function. I think it will take 1-2 minutes, and then it will stop. Okay. As I told you before, animation is an additional process usually. It is not that important as the minimization process itself, but really it gives you some, now it is already finished, it gives you some confidence and shows you how the things are working. So as you see, this is now first look how the number of the contours has increased and approaches closer and closer to the zero. Here is the zero area. Here is number 100. It will be, as I told you. So we are closer and closer to the zero value here. And here is the other photo or plot which we use by the HTML. Now, if we go to the file, Rosen, I think Rosen 3, like that. Now I shall see it. Rosen 3 GIF, here it is. And you press it here. You shall see this is the black and the blue and the arrows are converging slowly and slowly to the minimum value of the function. Because I have written repeat is allowed, so now it will repeat the whole cycle. Look how beautiful really it is working and how exactly they are converging to the minimum value which we have already suggested and calculated in advance as the minimum value. So as you see, really, the PSO algorithm works very fine. Animation now is in your hands. You can use the algorithms which I have explained to you for any function. Working with the PSO does not require that this function will be differentiable or should be convex or not. They are ready to be used for any function. I think with this work we finish to the lecture. Everything is okay and exactly working. Thank you very much for listening and see you in the coming lecture.